Hi, in this we are setting up a simple setup for demonstrating electromagnetic induction. This phenomenon occurs when a changing magnetic field induces an electromotive force, EMF, or voltage in a nearby conductor, such as a copper wire. Here's a breakdown of the setup. 1. Magnet. You have a magnet with north and south poles. When the magnet moves or changes position, it creates a changing magnetic field around it. 2. Copper wire coil. You have a coil of copper wire placed in the vicinity of the magnet. The coil is usually wound around a core, could be air or another material, to enhance the effect. 3. Movement. When you move the magnet or swing it, the magnetic field around the magnet changes. This change in magnetic flux through the coil induces an electromotive force, EMF, or voltage across the ends of the coil, according to Faraday's law of electromagnetic induction. 4. Voltage induced. As a result of the changing magnetic field, an electric current is induced in the copper wire. This induced current creates a voltage across the ends of the coil. 5. Swinging motion. The swinging motion of the coil is creating a dynamic change in the magnetic field, which enhances the electromagnetic induction effect. This is similar to how a generator works, converting mechanical energy, motion of the coil, into electrical energy, induced voltage. The induced voltage can be measured across the ends of the coil using a voltmeter. This simple setup is a basic illustration of how generators produce electricity through the principle of electromagnetic induction. Principle. Faraday's law describes the relationship between a changing magnetic field and the induction of an electromotive force, EMF, in a nearby conductor. Formula. The induced EMF is directly proportional to the rate of change of magnetic flux, where the negative sign indicates the direction of the induced current according to Lenz's law. Magnetic flux. Magnetic flux is the product of the magnetic field strength and the area through which the magnetic field lines pass. Mathematically, change in flux. Faraday's law emphasizes that it is the change in magnetic flux over time that induces an EMF. A constant magnetic field or static conditions do not induce a voltage. Direction of induced EMF. Lenz's law states that the induced current, and EMF, will always oppose the change in magnetic flux that produced it. This helps to maintain the conservation of energy. Applications. Faraday's law is the fundamental principle behind the operation of generators, transformers, and various electrical devices that rely on electromagnetic induction. Units. The unit of magnetic flux is typically measured in Weber, WB, and the induced EMF is measured in volts, V. Inverse relationship. There is an inverse relationship between the rate of change of magnetic flux and the electrical resistance of the conductor. Higher resistance leads to a smaller induced current. Experimental observation. Michael Faraday formulated this law based on his experiments, demonstrating that a changing magnetic field produces an electric current in a nearby conductor.